This video is going to show an example of decoding some serial data on the oscilloscope. This particular module is a RFID card reader, 120-ish kilohertz reader. It's the lowest frequency standard. And I'll just kind of get into what we see on the scope and then dive into it a little bit. So here we can see if I shine or present this card in front of this antenna, the scope shows some sort of output on the TX of the serial data port. And if I just change this to single capture mode so we can slow it down, we can observe exactly what we're seeing. So this is what comes up every time we present the card. The antenna receives some sort of interference signal from a chip inside this card. There's a processor on here, this chip here, that kind of interprets that data and then sends it out as serial. And so let's look at what the serial data is. It's just a bunch of pulses, and if I can actually use my scope to decode this, and we get this in binary, in decimal, because of the binary. So if we actually look at what the RS-232 standard does in this case, is we have a start bit, which means it goes low. Then we have our data. So in this particular example, let me zoom into what we were seeing. We have our start bit, and then it's 0, so this width is actually 2 bits wide. Let me adjust the time scale so that one division is just about 2 bits. Okay, so now we see each bit is about 100 microseconds if one width is 200. So we have our start bit going to 0, then a 0 bit, and then a 1 bit here, and then 6 more 0 bits, so 1, 2, 3 divisions, and then a stop bit, which brings the data back high. And then we continue to our next bit, which starts again as a start bit going down to 0. The second byte happens to also have the first bit of 0, and then it has its data. And if we decode it, we see it's a 2 if we are telling the scope to decode it as LSB first, as we see here. Which just means we treat this first bit as 2 to the 0, then 2 to the first, 2 to the second, and so on. Or it's 64 if we tell it that we want to interpret the most significant bit first. So it'd be 2 to the 7th, 2 to the 6th, 2 to the 5th, and so on. And it's supposed to be 9600 baud, but if we look at the actual amount of bits we're seeing, if we say in this byte sequence, the time it takes from here to here, the end of the stop bit, or to get better precision, we can measure 2 bytes worth of time. We see that's about 2.03 milliseconds. And 2 bytes, 16 bits, that's only about 7,800 kilobaud. So it actually turns out the 9600 comes from including the start and stop bits as well. And it's not even exactly 9600, but it's close enough. You can even tell the scope to interpret it as more than 9600, and it'll still work here. And then I mentioned this is a 125 kilohertz RFID module, so there's no 125 kilohertz yet, but if we actually look at the antenna, I have another probe in blue showing the antenna as well, and this frequency is actually 120 something kilohertz, 128, so close enough to the 125 that it's specified as. And we see that if we present the card to the reader like so, the chip actually takes power from this, and the way it communicates its information is it attenuates the signal in a similar bit pattern of 1s and 0s. So if I single capture this again so we can see the bit pattern. Let me get it more in depth. There we go. We can see we're actually amplitude shift keying the bits as well in the antenna. And the reason it doesn't line up with channel 1 and 2 is because it takes time for the processor to actually interpret this amplitude shift keying and then spit it out as RS-232.